సరిగ్గా కనపడుతుంది చూడు. సైలెంట్లో పెట్టావా? మెమరీ ఇమేజా? Good afternoon, students. How are you? Okay, be safe, stay at home. This is the revision class for outgoing seniors and long-term students. Okay, and yesterday we discussed thermometry, temperature scales, and conversion of temperature scales, temperature from one scale to another scale. Today I focus on explanation of solids. Okay, explanation of solids. Generally, solids expand on heating. It means when we supply heat energy to a solid, solids expand. But there are some exceptions. Generally, solids expand on heating, but plastic, rubber, some other metal, some other substances contract on heating. Most of the solids expand on heating, but plastic and rubber contract on heating. These are some of the exceptions. Based on the thermal expansion, solids can be classified into two categories. Some of the solids expand equally in all directions, so those are called as isotropic solids. Isotropic. Isotropic solids means the solids which expand equally in all directions on heating are called as isotropic solids. Most of the metals are isotropic in nature. And the solids which expand unequally in different directions on heating are called as anisotropic solids. So these solids do not expand equally in all directions, so those are called as anisotropic solids. So in different directions their expansions are different. Best example, Iceland spa. Okay, so we deal isotropic solids only. For example, consider a solid, and if heat energy is supplied to the solid, it expands. So, and first of all, I consider the one dimension, in one direction only, in one dimension. That means I am considering length. So, for example, consider a rod, and the initial length of the rod is L1. Here L1 is initial length of the rod, and it is measured at T1 degree centigrade. So L1 is initial length of the rod at T1 degree centigrade, and if we supply heat energy, that means internal energy increases. Because of that, the intermolecular distance increases. So that means the length of the rod increases. Maybe if some heat energy is supplied to the rod, the temperature of the rod increases to T2 degree centigrade. T1 is initial temperature and T2 is final temperature, and L2 is final length. Okay, L2 is final length, and experimentally it is observed that this linear expansion L2 minus L1 is proportional to its initial length when the nature of the material and change in temperature are kept constant. This relation experimentally observed by keeping the temperature temperature difference constant for the same type of material. That means nature and temperature difference are kept constant. Experimentally, it is observed that the linear expansion in the rod is directly proportional to its initial length. And when initial length and nature kept constant, nature of the rod kept constant, and it is observed that L2 minus L1 is directly proportional to change in temperature. So in the second case, the linear expansion is directly proportional to change in temperature when initial length and nature of the rod kept constant. So I have written two mathematical expressions, L2 minus L1 proportional to L1 and L2 minus L1 proportional to delta T. It means that T2 minus T1. So by combining these two mathematical equations, I can write L2 minus L1 equal to some proportionality constant into L1 into T2 minus T1. Okay, so that proportionality constant is taken as alpha. Here alpha is a constant that is named as coefficient of linear expansion of material. Okay, so here alpha is called as coefficient of linear expansion of the material, and from this mathematical expression I can write alpha equal to L2 minus L1 by L1 into T2 minus T1. Okay, so the coefficient of linear expansion of a material can be written as alpha equal to, alpha equal to L2 minus L1 by L1 into T2 minus T1. The coefficient of linear expansion of the material is denoted by alpha. Alpha equal to L2 minus L1 by L1 into T2 minus T1. Here L1 is initial length of the rod, L2 is final length of the rod, T1 initial temperature, T2 final temperature, or L2 minus L1 is also named as change in length, and T2 minus T1 is called as change in temperature. The CGS unit of change in length is centimeter, and the CGS unit of initial length is centimeter, and temperature is degree centigrade. Centimeter get cancelled, so and the CGS unit of alpha is degree centigrade inverse, and the SI unit of coefficient of linear expansion is Kelvin inverse. Okay, so here in the problem, in the numerical problems, alpha can also be written as alpha equal to delta L by L into delta T. So here delta L is change in length and delta T is change in temperature. So here from this expression we can write delta L change in length or linear expansion can also be written as delta L equal to alpha into L into delta T. Here delta L is called as linear expansion or linear change in length of the rod. So here alpha depends on nature of the material. For steel 12 into 10 power minus 6 per degree centigrade. For brass 18 into 10 power minus 6 per degree centigrade. So alpha is in the order of 10 power minus 6 per degree centigrade, and alpha depends on nature of the material, and alpha depends on the scale of temperature that we choose. Because if we consider T1 and T2 in Fahrenheit scale of temperature, alpha is different. So the change in length delta L equal to alpha into L into delta T, and from this mathematical expression we can write delta L by L. So mathematically, and this can be read as fractional change in length. So fractional change in length delta L by L equal to alpha into delta T. న్యూమరికల్ ప్రాబ్లమ్స్ లో ఫ్రాక్షనల్ చేంజ్ ఇన్ లెంత్ అని అడిగితే డెల్టా ఎల్ బై ఎల్ కనుక్కోమని అర్థం. అండ్ పర్సంటేజ్ చేంజ్ ఇన్ లెంత్, దిస్ ఈజ్ కాల్డ్ యాజ్ పర్సంటేజ్ చేంజ్ ఇన్ లెంత్. సో left hand side is multiplied with 100, so right hand side also should be multiplied with 100. This is named as percentage change in length. So percentage change in length equal to alpha into delta T into 100. Okay, అంటే ప్రాబ్లమ్స్ లో మనకి ఇన్ని రకాలుగా అడగొచ్చు. This is fractional change in length and this is percentage change in length. Okay, alpha into delta T into 100. Alpha depends on nature of the material and alpha depends on the scale of temperature that we choose. Scale of temperature that we choose. Okay, next. So alpha equal to delta L by L into delta T. Alpha equal to delta L by L into delta T, and for different materials it has different values. Next, for example, yesterday I discussed that the relation between centigrade scale of temperature and Fahrenheit scale of temperature, that is C by 100 equal to F minus 32 by 180. So C equal to 100 by 180 into F minus 32. C equal to 5 by 9 into F minus 160 by 9. 2 5s, 2 9s, and 5 by 9 is multiplied with F and 32. Okay, already you know that differentiation. So delta C equal to 5 by 9 into delta F minus differentiation of constant is 0. So this is the relation between change in temperature in degree centigrade. Delta C is change in temperature in degree centigrade and delta F is change in temperature in Fahrenheit scale when temperatures are measured in Fahrenheit scale of temperature. So here, if the temperature is measured in centigrade scale and the coefficient of linear expansion is considered as alpha C, and when temperatures are measured in Fahrenheit scale, the coefficient of linear expansion is taken as alpha F. Alpha C is coefficient of linear expansion when temperature is measured in degree centigrade, and alpha F is coefficient of linear expansion when temperature is measured in Fahrenheit scale. So alpha C and alpha F. Now we can relate alpha C and alpha F. For example, for same L1 and delta L, and alpha depends on change in temperature. Okay, delta C equal to 5 by 9 into delta F. So alpha C equal to, for example, alpha C equal to delta L by L into delta C. and alpha F can also be written as delta L by L into delta F. Okay, so in the place of delta C, I can write 5 by 9 delta F. So alpha C equal to 9 by F into alpha F. Okay, this is the relation. So alpha C is temperature, coefficient of linear expansion when temperature is measured in alpha C is measured in alpha C is coefficient of linear expansion when temperature is measured in centigrade scale. Alpha F is coefficient of linear expansion when temperature is measured in Fahrenheit scale of temperature. Next, if we consider the two-dimensional object means it has length and breadth, so we have to consider the area. So if we consider the expansion of the solid in two dimension, we have to consider the concept of area. So, and that is called as coefficient of areal expansion. Coefficient of areal expansion is also named as coefficient of superficial expansion. It is denoted by beta. Beta equal to A2 minus A1 by A1 into T2 minus T1. Here A1 is initial temperature, A1 is initial area, A2 is final area, T1 is initial temperature and T2 is final temperature, and beta equal to A2 minus A1 by A1 into T2 minus T1, and here A2 minus A1 can be written as beta into A1 into T2 minus T1, or delta A by A is fractional change in area. Fractional change in area equal to beta into delta T, and percentage change in area delta A by A into 100 equal to beta into delta T into 100. This is percentage change in area and this is fractional change in area. So beta depends on the nature of the material and scale of temperature choose, and beta C equal to 9 by 5 into beta F. Okay, so beta C is coefficient of areal expansion when temperature is measured in centigrade scale, and beta F is coefficient of areal expansion when temperature is measured in Fahrenheit scale. Okay, next one, consider the three-dimensional object, three-dimensional solid. So if we consider the three-dimensional solids, it has length, breadth and height. So I have to consider the volume. So if I consider the volume, that is gamma equal to V2 minus V1 by V1 into T2 minus T1. Here gamma is called as coefficient of volume expansion of a solid. It is also named as coefficient of cubical expansion of a solid. Gamma equal to V2 minus V1 by V1 into T2 minus T1. Alpha, beta and gamma has a Celsius units of per degree centigrade. Alpha, beta, gamma has SI unit of Kelvin inverse. So from this I can write the change in volume V2 minus V1 equal to gamma into V1 into T2 minus T1. Here V1 is initial volume of the solid, V2 is final volume of the solid, T1 is initial temperature, T2 is final temperature. So, and delta V is change in volume of the solid, delta V by V equal to gamma into delta T. Here delta V by V can be read as fractional change in volume. The fractional change in volume delta V by V equal to gamma into delta T, and percentage change in volume delta V by V into 100 equal to gamma into delta T into 100. This is percentage change in volume of the solid. Percentage change in volume of the solid is given by gamma into delta T into 100. So gamma depends on nature of the material and scale of the temperature chosen. So gamma C can be written as 9 by 5 into gamma F. So gamma C is coefficient of volume expansion of the solid when temperature is measured in centigrade scale. Gamma F coefficient of volume expansion or cubical expansion when temperature is measured in Fahrenheit scale of temperature. Okay, next this is about the basics of expansion of solids alpha, beta and gamma, and there is relation between alpha and beta, and you have the derivation in your IP. So beta equal to 2 alpha. The relation between alpha and beta is given by beta equal to 2 alpha, and the relation between alpha and gamma is gamma equal to 3 alpha. So all these formulae meant for isotropic solids. Isotropic solids means the solids which expand equally in all directions. So, and the relation between beta and gamma. So in the place of gamma equal to 3 into alpha, in the place of alpha I can write beta by 2. So this is the relation between gamma and beta, gamma equal to 3 beta by 2. So finally the relation between alpha, beta and gamma, the relation between alpha, beta and gamma is alpha is to beta is to gamma equal to, in the place of alpha I write alpha, in the place of beta I write 2 alpha, in the place of gamma I write 3 alpha, and alpha get cancel, so 1 is to 2 is to 3. So the relation between alpha, beta and gamma is alpha is to beta is to gamma equal to 1 is to 2 is to 3. Okay, beta equal to 2 alpha, gamma equal to 3 alpha, and alpha is to beta is to gamma equal to 1 is to 2 is to 3. And for anisotropic solids, for example, anisotropic solids means they expand unequally in different directions. They expand unequally in different directions. For example, if I consider and a three-dimensional figure, and alpha x is coefficient of linear expansion of anisotropic solid along x direction, and alpha y is coefficient of linear expansion in y direction, and alpha z is coefficient of linear expansion in z direction. So the average value of alpha can be written as alpha equal to alpha x plus alpha y plus alpha z by 3. Okay, so for anisotropic solids, but our syllabus meant for most of our syllabus meant for isotropic solids only, and for anisotropic solids, if in 3 different directions, x-axis, y-axis and z-axis, and alpha x, alpha y, alpha z coefficient of linear expansions are given, then the average value of coefficient of linear expansion alpha equal to alpha x plus alpha y plus alpha z by 3. Okay, next now we discuss some of the applications of expansion of solids. The first application. If we observe rails, a small gap is left between the two rails. While constructing a railway track, a small gap is left between the two rails because to allow thermal expansion. So the gap, if L is the length of each rail and delta T is change in temperature, so the gap that should be left between the two rails can be written as delta L equal to L into alpha into delta T. So scientists they calculate that if they know the alpha value and approximate value of delta T, and they can measure the L value, from that they can calculate delta L value. From that and they left some gap between the two rails. So a small gap is left between while constructing a railway track because to allow thermal expansion, and the gap that should be left between the two rails is given by delta L equal to L into alpha into delta T. Okay, next one. Second application, pendulum clocks. Pendulum clock. And in our day-to-day life we observe that some of the pendulum clocks generally pendulum is made up of with some of the material. Okay, pendulum is made up of with some of the material, and if they manufactured in at a temperature of 30 degrees centigrade and it is using at a temperature of 40 degrees centigrade, maybe because of change in temperature, maybe it expand, length increases. Before that I explained some basic concept of a simple pendulum. A metal bob is suspended to a light string is called as a simple pendulum. This is the center of mass of the bob and this is the point of suspension. Okay, the distance between the point of suspension and the center of mass of the bob is called as length of the simple pendulum. The distance between the point of suspension and the center of mass of the bob is called as length of the simple pendulum. Generally, length of the simple pendulum is denoted by L. And actually, if I consider this is a simple pendulum and this position is mean position, and if I move it aside and releases, it makes oscillations, and these are the extreme positions. So if the simple pendulum move to a side and reaches the extreme position and come back to that mean position and move to that another side, reaches the extreme position, and again if it come back to that initial position, that means one oscillation. The time taken to complete one oscillation is called as time period. Generally, time period is denoted by T. You know the expression for time period of simple pendulum t equal to 2 pi into root of L by G that you studied in oscillations chapter. The time period of oscillations of a simple pendulum t equal to 2 pi into root of L by G, and in that chapter you studied about seconds pendulum also. A simple pendulum whose time period is equal to 2 seconds is called as seconds pendulum. So t equal to 2 pi into root of L by G. Here L is length of the simple pendulum, G is acceleration due to gravity. So at a given place the value of G is constant. So if G is constant, when G is kept constant and T is directly proportional to root L. When G is kept constant, T is directly proportional to root L. It means that if there is increase in length of the simple pendulum, there will be increase in time period also. If there is decrease in the length of the simple pendulum, there will be decrease in time period of the simple pendulum also. For G kept constant, the time period of simple pendulum is directly proportional to root L. Okay, so keep it in mind. So for example, here the pendulum clock is manufactured at 30 degrees centigrade and it is used at 40 degrees centigrade. Pendulum clock is made at a pendulum clock shows correct reading at 30 degrees centigrade, but it is using at 40 degrees centigrade. That means temperature increases. Temperature increases. Okay, so if temperature increases, obviously the length of the simple pendulum, length of the pendulum clock increases according to the thermal expansion of solids. So as temperature increases and length of the pendulum clock also increases. If length of the pendulum clock increases, time period increases. Already just now I have written T proportional to root L. As length of the pendulum increases, time period also increases. Time period increases means previously it takes 1 second to complete one oscillation. Now it will take 1.5 seconds to complete one oscillation. 1.5 or 1.6, more than 1. So watch moves slowly. Watch moves fast. So as temperature increases, length of the pendulum increases, hence time period increases. Time period increases means time period increases. Actually the original time period of oscillation is 1 second. Now it will take 1.5 seconds. So watch moves slowly. If watch moves slowly, there is a loss in time. Actually అయితే ఎంట్రన్స్ ఎగ్జామ్ కి రెండు చాప్టర్స్ రెండు కాన్సెప్ట్స్ లింక్ పెట్టే ప్రాబ్లమ్స్ చాలా ఈజీ. ఇది సింపుల్ హార్మోనిక్ మోషన్, ఎక్స్పాన్షన్ ఆఫ్ సాలిడ్ లింక్ పెట్టే కాన్సెప్ట్ కాబట్టి ఇది కొంచెం ఇంపార్టెంట్ ఈ టైప్ ఆఫ్ ప్రాబ్లమ్స్. So as temperature increases, length of the pendulum increases, hence time period increases. So watch moves slowly, there is a loss in time. After that I discuss, I calculate the loss in time. Next, the pendulum clock is calibrated at 30 degrees centigrade and it is using at 20 degrees centigrade. That means temperature decreases and it contracts, length of the pendulum decreases. If length of the pendulum decreases, time period also decreases because t proportional to root L. So previously the time period of oscillation is 1 second. Now it is taking 0.8 seconds only. So watch moves faster. So if watch moves faster, there is a gain in time. There is a gain in time. Okay, so loss or gain in time per second, and actually according to expansion of solids, alpha can be written as delta L by L into delta T. Okay, so loss or gain in time, loss or gain in time per second equal to 1 by 2 into alpha into delta T. Here alpha is coefficient of linear expansion, delta T is change in temperature. Loss or gain in time per second. Yeah, once again I am repeating, as temperature increases, the length of the pendulum increases, time period increases, watch moves slowly, there is loss in time. As temperature decreases, length of the pendulum decreases, hence time period decreases, watch moves fast, there is gain in time. So loss or gain in time per second can be calculated as 1 by 2 into alpha into delta T. Okay, 1 by 2 into alpha into delta T. So in the case of pendulum clocks, in the case of pendulum clocks, loss or gain in time per second equal to 1 by 2 into alpha into delta T. 1 by 2 into alpha into delta T. Next, loss or gain in time per minute equal to 1 by 2 into alpha into delta T into 60 seconds. Next, loss or gain in time per hour equal to 1 by 2 into alpha into delta T into 60 seconds. Loss or gain in time per day equal to 1 by 2 into alpha into delta T into 60 into 24 seconds. So which is equal to 1 by 2 into alpha into delta T into 86,400 seconds. So this is a very important formula. The law in the case of pendulum clocks, loss or gain in time per day equal to 1 by 2 into alpha into delta T into 86,400 seconds. This is about pendulum clocks. Next application, thermal stress. For example, consider a metal rod that is rigidly fixed between two walls, and if it is heated, if heat energy is supplied to it and it expands, so obviously there is no allow of thermal expansion easily. so it applies some force on it. Force per unit area is called as stress. Okay, so and stress is nothing but force by area, and strain is nothing but linear longitudinal strain is delta L by L. And here we are giving some heat energy to the solid, so alpha can be written as alpha equal to delta L by L into delta T, and the ratio of stress to strain is called as modulus of elasticity. The ratio of longitudinal stress to the longitudinal strain is called as modulus of Young's modulus. From this we can write delta L by L. Delta L by L equal to F by A into Y. So in the place of delta L by L, I can write F by A into Y into delta T. So F by A is nothing but alpha into Y into delta T. So this is nothing but thermal stress. Thermal stress is Y alpha delta T, or force due to thermal stress F equal to Y A alpha delta T. A solid is rigidly fixed between the two walls, and some heat energy is given to it, and some stress is developed, some force is exerted on the walls, so that force is due to the thermal energy. So thermal stress, this is called as thermal stress. Thermal stress equal to Y alpha delta T, or force due to thermal stress F equal to Y A alpha delta T. This is another application of expansion of solids. Okay. Next, metal tapes.